This is the 14th video in a series devoted to Introduction to Proofwriting. And today we're going to start talking about mathematical induction. So mathematical induction is a strategy for proving a family of mathematical statements is true, where that family is indexed by the natural numbers, or sometimes more generally the integers. Okay, so let's dive into an outline of a proof by mathematical induction, and then we'll kind of give some intuition for why it works. So let's suppose that you want to prove the following proposition. It says, for all natural numbers n, p of n is true. Well, it just says p of n, but that's understood to mean p of n is true. So that means you've got a bunch of mathematical statements, p of 1, p of 2, p of 3, p of 4, so on and so forth. And they're all probably connected in some sort of way. And we'd like to prove that they're all true. Okay, so here's our strategy. We'll prove something called the base case. And the base case is the first case of this identity or statement or whatever it is. So we'll prove that the statement p of 1 is true. And I'd like to point that out that we could do this any way we want, with a proof by contrapositive, contradiction, a direct proof, whatever we need to do. And then after that, we'll do something called the induction step. And for the induction step, we'll say that we are given some arbitrary k bigger than or equal to 1, and we'll prove that the truth of pk implies the truth of pk plus 1. So I'd like to point out that assuming this pk is true is sometimes called the induction hypothesis, and then proving this conditional is known as the induction step. But I think we can all put it into an induction step. So I guess it's important to point out that this is a conditional, so you would prove this with methods for proving conditionals like we've done before. Okay, so the standard visualization of a proof by induction is with a set of dominoes. So let's say we've got infinitely many dominoes, and those dominoes are indexed by the natural numbers, and each of them is attached to a statement. So this is the domino P1, P2, P3, so on and so forth. So I like to think about the base case as pushing over domino P1. Okay, so we've pushed over domino P1. And then the induction step, which shows that pk implies pk plus 1, is like checking that the dominoes are close enough together so that one knocks over the next one. So if this induction step holds, then pushing over p1 will push over p2, which will push over p3, which will push over p4, and so on and so forth. But it's important to do both of these. If we check that the dominoes are close enough together without pushing over the first domino, then we haven't done anything. So that's why the base case is important. But if we've pushed over the first domino without checking that the dominoes are close enough together, then all we've done is pushed over the first domino. That's why this induction step is important. So these two together will prove this infinite family of mathematical statements. Okay, so for the remainder of the video, I essentially want to do just a bunch of examples of proof by induction. And then there'll be a follow-up example video with even more of these. And if you're in the class I'm teaching, you're going to do a ton of these in class. I think maybe we'll just use the method of greasing the groove to get the real feel for proofs by induction. Okay, so let's look at our first statement. We'd like to prove for all natural numbers n that the sum 1 plus 3 plus 5 plus 7 plus 9 plus 11 all the way up to 2n minus 1 is equal to n squared. So this is the sum of the first n odd natural numbers is equal to n squared. So that's pretty interesting. Okay, so let's prove this by induction. So I'm going to lay this out by stating that we're doing the base case first. But this is really a chalkboard way to write this down, or maybe a rough draft way to write this down. If you were to write this down as a final draft, it would be like in a paragraph form. So maybe look back at your rules for writing mathematically to see how you might want to edit it into a final version. Okay, so our base case will be the n equals 1 case here. And notice the n equals 1 case is simply 1 equals 1 squared. So that's okay. Notice that if we're just summing the first natural number, the first odd natural number, that's just 1. And the first square of the odd natural numbers is just 1 also, so 1 squared. So we're good to go there. Okay, so now let's make our induction hypothesis. So in other words, we will assume that pk is true. So again, I will just lay this out. So our induction hypothesis is, let's suppose for some k bigger than or equal to 1, we have 1 plus 3 plus 5 all the way ending at 2k minus 1 equals k squared. So if we're doing our conditional over here, if pk, then pk plus 1, this is like assuming that pk is true. Now we want to show that this leads to pk plus 1 being true. Okay, so let's see how we can do that. So now we'll consider the next case, but we'll only consider the left-hand side of this next case. So that'll be 1 plus 3 plus 5 plus 2k minus 1 plus 2k plus 1. So let's notice that's the next odd natural number. So if the kth odd natural number is 2k minus 1, then the k plus first is 2k plus 1. And I guess maybe we can notice that by seeing that this is equivalent to 2 times the quantity k plus 1 minus 1. Okay, great. But now we can use our induction hypothesis to take this first bit and rewrite it as k squared. So this is equal to k squared plus 2k plus 1 by the induction hypothesis. So let's color code this. All of that stuff in the green underline is collapsing to this k squared by our induction hypothesis. And then we're simply bringing down this k plus 1, or 2k plus 1. But now that clearly factors as k plus 1 squared, so we have this as k plus 1 squared. But that's exactly what we wanted to do. The sum of the first k plus 1 odd natural numbers is k plus 1 squared, so that finishes our proof by induction. So let's just reiterate what we've done here. Notice that at this step here, we supposed that pk was true, and down here we showed that that led to pk plus 1 being true. Okay, let's do another. So our next example will be an alternating version of our first example. So in particular, we'll show for all natural numbers n, this alternating sum, minus 1 plus 3, minus 5 plus 7, all the way up to minus 1 to the n, 2n plus 1 is equal to minus 1 to the n times n. And we'll do this exactly the same way by proving the base case and then doing the induction step. Okay, so let's see our base case here. That is also the n equals 1 case. So let's see what happens with the n equals 1 case. We have minus 1 is the same thing as minus 1 to the 1 times 1. So we're good to go there. Notice the base case is generally quite simple. Okay. So now let's make our induction hypothesis, which is that the kth case is true. Okay, so let's suppose for some k bigger than or equal to 1, we have our statement is true. So in other words, we have minus 1 plus 3 minus 5 plus 7 all the way up to plus minus 1 to the k times 2k minus 1 equals minus 1 to the k times k. Okay, then that's like our kth statement being true. We're assuming pk in this conditional. Now we'd like to use this to prove pk plus 1. So let's consider the left-hand side of the k plus 1 case. So that will be minus 1 plus 3 minus 5 plus 7 minus all the way up to plus minus 1 to the k times 2k minus 1, and then plus minus 1 to the k plus 1 times 2k plus 1. So here we have the first k terms alternating, and then we've got the k plus first term there. Okay, and now let's color code our simplification again. So this purple underline will collapse to something quite simple using our induction hypothesis. In fact, it will collapse to minus 1 to the k times k using, like I said, our induction hypothesis. So let's underline that. And then we'll simply bring this term down. So we'll have plus minus 1 to the k plus 1 times 2 to the k, or times 2k plus 1. Now what we'd like to do is factor a minus 1 to the k plus 1 out and see what we're left with. So factoring a minus 1 to the k plus 1 out of this whole thing, let's notice that this k will be attached to a minus 1, so we'll have a minus k. So I think that's pretty clear because we're essentially just dividing by minus 1 there. And then we'll have plus 2k plus 1 left over from the second term. But now that simplifies quite nicely to minus 1 to the k plus 1 times k plus 1, which is exactly where we needed this to end to finish this proof by induction. Okay, let's do another. For our next example, we'll prove for all natural numbers n to the 5th power is congruent to n mod 5. So this is indeed a special case of Fermat's little theorem, just for what it's worth. Okay, so let's get going. So we'll do this by induction, like we said. So let's do our base case. So our base case is the n equals 1 case. Well, let's notice that 1 to the 5 is equal to 1. Well, 1 raised to any power is equal to 1, but 1 is definitely congruent to itself mod 5. And that's because 5 divides 1 minus 1. 5 divides 0. 0 is clearly a multiple of 5. It's the trivial multiple of 5. Okay, great. So now let's make our induction hypothesis. So let's suppose for some k bigger than or equal to 1, we have the result. So in other words, k to the 5th is congruent to k modulo 5. Great. And now what we want to end up with is k plus 1 to the 5th is congruent to k plus 1 mod 5. But we have to get there. And in order to get there, we need to recall what it means for numbers to be congruent mod n or congruent mod 5. So let's recall that up here. So A is congruent to B mod, I'll just say 5, if and only if 5 divides A minus B. So that's what we'll use. We will actually show that 5 divides k plus 1 to the 5th minus k plus 1. Okay, so that means we need to look at k plus 1 to the 5th minus k plus 1. Okay, so anyway, let's consider that. So let's consider k plus 1 to the 5th minus k plus 1. Again, motivated by the fact that we need to look at the k plus first case and this definition of congruence mod 5 up here. Now let's expand some things out and see what we have. So we'll have k to the 5th plus 5k to the 4th plus 10k cubed plus 10k squared plus 5k plus 1. So that's what we get if we take k plus 1 to the 5th power. We know how to do that quickly by using binomial coefficients. So this is 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and 5 choose 5. Okay, so from this object, we will subtract k plus 1. Okay, so let's see what that leaves us with. So that will leave us with k to the 5th minus k, where I've put the k to the 5th here and this minus k together. You might say, well, why didn't I combine like terms with this 5k term? That's because I want to use my induction hypothesis. Okay, so anyway, I've got k to the 5th minus k, and then everything left over will be a multiple of 5 because those 1's cancel. So let's factor a 5 out. So we'll have plus 5 and then k to the 4th plus 2k cubed plus 2k squared plus k. Okay, great. So that's the simplification that we've done here. But let's notice that this is most definitely a multiple of 5. And this is a multiple of 5 as well by the induction hypothesis. So in the end, we know that this whole thing is a multiple of 5. So this is equal to 5m for some m, which is an integer. Again, because we've got a multiple of 5 here by the induction hypothesis, and we have a multiple of 5 here like by construction. Okay, but now putting this together, we see that 5 divides k plus 1 to the 5th minus k plus 1. Just reading this from the extreme left to right-hand side. But that's exactly the same thing as saying k plus 1 to the 5th is congruent to k plus 1 modulo 5. But that's exactly where we wanted to end this thing up. Okay, let's do another. Next up, we've got a nice calculus problem, and it's something that you learned in calculus class, but I think it's nice to reinvestigate it now that we know a little bit about induction. So let's assume the product rule and that the derivative with respect to x of x is 1. And then our goal is to show that the derivative with respect to x of x to the n is n times x to the n minus 1. So that's the power rule for natural number exponents. Okay, so we'll do this just like we've done the others. Let's first look at the base case. Notice the base case is done here by the given. So notice that it's given right here. We are assuming that the derivative with respect to x of x to the 1 is 1 times x to the 0. So this is done. You know, and sometimes this will be the case. Okay, so now let's make our induction hypothesis. So that will be for some k bigger than or equal to 1, we have the derivative with respect to x of x to the k is k times x to the k minus 1. And then from here, let's consider the next case. So let's consider the derivative with respect to x of x to the k plus 1. But now we can use exponent rules for multiplying powers of x to rewrite this as the derivative with respect to x of x times x to the k. And then from here, we'll use the product rule, which is sometimes more formally known as the Leibniz rule. So this will give us the derivative with respect to x of x times x to the k plus x times the derivative with respect to x of x to the k. So the derivative with respect to x of x is 1, so that leaves us with x to the k plus x times k times x to the k minus 1 using the induction hypothesis. But now putting this all together and simplifying, you'll see that we get exactly what we want, that we have k plus 1 times x to the k. Okay, let's do another. So our next example is a special case of something known as Bernoulli's inequality. So you can look up the general setting of Bernoulli's inequality if you're psyched. So what we'll show is that for all real numbers x bigger than or equal to -1 and natural numbers n, we have 1 plus x to the n is bigger than or equal to 1 plus n times x. So if x were positive here, we could use binomial expansion. It'd be quite nice. But here we're allowing certain negative values of x. Okay, so let's get into it. So our base case will be the n equals 1 case, just as normal. So it won't always be the n equals 1 case. You could envision a time where we start at n equals 0 or n equals 2 or n equals 3, just if we don't have all of the statements. But for everything that we've seen, we've used n equals 1 as our starting point. Okay, so let's look at 1 plus x to the 1 power is equal to 1 plus 1 times x, but that is bigger than or equal to 1 plus 1 times x. So there, we've done it. There's not much to do there. So now let's make an induction hypothesis. So following the same kind of strategy, let's suppose for some k bigger than or equal to 1, we have the statement is true. So in other words, 1 plus x to the k is bigger than or equal to 1 plus k times x. And then next up, we'll consider the k plus first case. So 1 plus x to the k plus 1, which is the same thing as 1 plus x times 1 plus x to the k. Notice it's always really important to take your next case, your k plus first case, and somehow manipulate it so that we can use the induction hypothesis. And that manipulation is usually quite simple. Just like here, we took 1 plus x to the k plus 1 and factored a 1 plus x out so that we had a 1 plus x to the k to work with. Okay, so now let's apply our induction hypothesis. So that makes this bigger than or equal to 1 plus x times 1 plus k times x. So again, that's our induction hypothesis. And then from there, we'll just multiply this out. So that will give us something like this. 1 plus k plus 1 times x plus k times x squared. So that's what we get when multiplying this out. But since k is a natural number and x is a real number, we know that this is bigger than or equal to 0. So if we drop it, we get something less than or equal to what we started with. So we get that our object is bigger than or equal to 1 plus k plus 1 times x. But now reading from here to here, you see that we have the desired equality or inequality to finish off this statement. Okay, let's move on to another example. Now we're going to look at a result related to the fundamental theorem of arithmetic. So let's suppose we have a list of integers a1, a2 up to an. N is bigger than or equal to 2, so we have at least 2 integers. And then let's also suppose we've got a prime, which I'll call p. Finally, let's suppose that p divides this product a1, a2 up to an. Then we'll show that it follows that p divides ai for one of these ai's, or for one of these i's between 1 and n. So notice that we can do this by induction, and our base case is the n equals 2 case here because we're not interested in the n equals 1 case based off the setup. So let's do our base case, which like I said is the n equals 2 case. So let's suppose that p divides a1 times a2. And then let's break this down into cases. So case number 1 is that p divides a1. And in that case, we're done because it divides one of the terms of the product. But case 2 will be that p does not divide a1. Okay, so we've got it must divide a1 or it must not divide a1. So that's pretty clear. But if it does not divide a1, then the GCD of p and a1 is equal to 1. So that's by the definition of the GCD and primeness. Okay, but if the GCD is equal to 1, then that tells us there exists integers x and y such that p times x plus a1 times y equals 1. So recall the GCD of two natural numbers can always be written as a linear combination of those natural numbers. I guess I should say an integer linear combination of those natural numbers. So now let's start using that p divides a1 times a2. So maybe I'll write it like this. So also, since p divides a1 times a2, we have a1 times a2 is equal to p times, I'll maybe use z for another integer. And now where would we like to go from there? Well, I think we'd probably like to get an a1 times y built in to this equation so that we can get the a1 out of there. Notice that I can rewrite this linear combination equation as a1 times y equals 1 minus px. So if I can eliminate the a1-ness from this, that would be good. So we can do that by multiplying this entire equation by y. So that'll give me a1 times y times a2 is equal to p times z. And then from there, I can make my replacement. So I'll replace a1 in this equation with 1 minus px. So that means I have 1 minus p times x times a2 is equal to p times z. But now let's move some things around. I have a2 is the same thing as p times z plus p times x times a2. So that's just from symbolic manipulation. But notice that equals p times z plus a2x. But that means that a2 is a multiple of p. In other words, p divides a2. Okay, so let's see what we have. Our first case was p divides a1, in which case we're done. Our second case was p does not divide a1, but that led us to p must divide a2. So that means that we do have p divides a1 or a2 as needed, but that's just for our base case. So now let's move on to our induction hypothesis. So now let's make our induction hypothesis. So let's suppose that if P divides A1 up to AK, then P divides AI for some I between 1 and K. So we're supposing that a conditional statement is true, so that's important. Okay, so now let's suppose that P divides A1 up to AK plus 1. And then let's break this into two cases. So case number one is that P divides AK plus 1. But in this case, we're done because we have P divides one of the terms from that product. Then case number two will be P does not divide AK plus 1. But then by the n equals 2 case, or by the base case, that means that P must divide the product A1 up to AK. Here we're thinking about splitting this product A1 up to AK plus 1 as A1 up to AK and then AK plus 1. Great. So we can really apply the base case to that larger problem. But now if P divides this product A1 up to AK, then by the induction hypothesis, that means P divides AI for some I between 1 and K. Okay, so let's see it. Either P divides AK plus 1, or it must divide one of the AIs between 1 and K, but that's exactly what we needed to finish this statement off. Okay, let's do one more example. For our last example, we'll use induction to prove the finite geometric series formula. And so that says for all real numbers x, we have the sum 1 plus x squared ending at xn equals 1 minus x to the n plus 1 over 1 minus x. Okay, so let's start with the base case. So notice our base case is the n equals 1 case. We'll have 1 plus x. But notice that's most definitely equal to 1 minus x times 1 plus x over 1 minus x. Just multiplying the numerator and the denominator by 1 minus x. And then we can multiply this out and get 1 minus x squared over 1 minus x. And I guess I see a little bit of a problem with my statement here, and that is I should not allow x to be equal to 1. So let's fix that there. So for all real numbers x that are not equal to 1. So anyway, we've done our base case. Now let's make our induction hypothesis. So let's suppose for some k bigger than or equal to 1, we have 1 plus x plus ending at x to the k is equal to 1 minus x to the k plus 1 over 1 minus x. Okay, good. Now let's consider the next case. So our next case will be the sum 1 plus x plus up to x to the k plus x to the k plus 1. Good. Now we'll apply our induction hypothesis to the first k terms, and that will leave me with 1 minus x to the k plus 1 over 1 minus x. So let's just point out that that's coming from our induction hypothesis. And then we have this last term, which is x to the k plus 1. Now let's give ourselves a common denominator. This is going to be 1 minus x over 1 minus x to give myself a common denominator. And then let's multiply some things out. So we'll have 1, then we'll have minus x to the k plus 1 plus x to the k plus 1. So those will cancel. And then we'll have x to the k plus 1 times minus x. That'll be minus x to the k plus 2. Then my denominator is still 1 minus x. But that's exactly where I needed to end to finish this proof by induction. Okay, now let's end with some warm-ups. So I've got 3 warm-up exercises based off what we saw today. So the first is to show that the sum of the first n squares is equal to n times n plus 1 times 2n plus 1 over 6. Next is this nice inequality involving powers of 2. We have 2n plus 1, 2 to the power n plus 1, is bigger than or equal to 2 to the power n plus 2 to the n minus 1 plus 1. And then finally, divisibility problem. Show for all natural numbers n that 3 divides 7 to the 2n minus 1. In other words, 7 to the 2n minus 1 is a multiple of 3, or if you want to work with congruence mod 3, that's the same thing as saying 7 to the 2n is congruent to 1 mod 3. So there might be a really simple way to do this, but recall that our goal here is to prove this by induction for practice. And that's a good place to stop.